Welcome. In this chapter, we will be discussing stereoisomerism, what that is, how to differentiate between structures, and how to represent them in three dimensions. Our learning objectives include differentiate between stereoisomers and constitutional isomers, compare rotational and reflectional symmetry, including descriptions of if and how an axis of symmetry and plane of symmetry affect chirality. Don't worry, we'll discuss that in detail as we move through the chapter. Describe how the configuration of a chirality center is assigned using the can-ingot prelock system. Draw Fisher projections. Compare effects of pairs of enantiomers on plane polarized light. Compare stereoisomers and diastereomers. Describe how stereo descriptors are assigned for certain trisubstituted and tetrasubstituted alkenes. Describe and calculate enantiomer excess. Explain the methods of resolution of enantiomers. Determine whether a compound with two rapidly interconverting conformations that are non-superimposable mirror images of each other is optically active. And lastly, describe how a compound can be chiral without containing a chiral center. Let's start by reviewing the definition of an isomer. When we talk about isomers, we're talking about different compounds that have the same formula. Usually, isomers fall into one of two categories, either constitutional isomers, which have the same molecular formula but different connectivity of atoms, or stereoisomers, same molecular formula and connectivity but different spatial arrangements of atoms. Although the two molecules below have the same connectivity, they are not identical, therefore they are stereoisomers. So in this case, we have 1,2-dimethyl cyclohexane. So we have cyclohexane, 6-member ring, as we saw from our last chapter, two methyl groups, one in position 1, one in position 2. Now when you are drawing this structure, you have two options. Either both methyl groups are on the same plane, either up or down, or the other option is that they're on different planes, up and down. When we have these options, then both compounds are different and they are possible, so we have to be able to differentiate between each of them in their names. For that, we use what we call the cis and trans prefixes. A cis prefix refers to having the substituents both on the same plane. A trans substituent is when you have them on opposite planes, like you do on the structure on the right. To maintain orbital overlap in the pi bond, carbon-carbon double bonds cannot freely rotate. So in that case, when you put a substituent in one place, because this bond right here can't really rotate, then these methyl groups in this example, they're actually kind of stuck in there. So you have either the two methyl groups in one place or they're on opposite planes. When they're the same plane, just like on the previous example, they're going to be the cis, in this case 2-butene, right? 2 to distinguish where that double bond starts. So 1, 2, 3, 4. And then the trans 2-butene, 1, 2, 3, 4. Cis-trans isomerism is only one type. There are other important stereoisomeric relationships. To identify such stereoisomers, we must be able to identify chiral molecules. That's going to be a big point throughout this chapter. We're going to be looking at that many times as we progress throughout the various sections. A chiral object is asymmetric, which means it is not the same as its mirror image, non-superimposable on its mirror image. You can test whether two objects are identical by seeing if they are superimposable. One example of non-superimposable with the mirror image will be your hands, right? Your right hand looks very, very similar to your left hand, but you can't really put one on top of the other, right? Because the thumbs will be on opposite sides. That's a good example of a non-superimposable. Chirality is important. And this is something that you will hear me say throughout this course and throughout the rest of chemistry, really. Structure will determine function. So how something is placed in 3 dimensions will give you a big idea as to how it behaves. That applies in material sciences. That also applies in biology. Biological systems are very, very sensitive to structure and how atoms are arranged in 3 dimensions. So in this case, because two chiral molecules are mirror images, they will have many identical properties, but because they are not identical, their pharmacology may be very different. Visualizing mirror images of molecules and manipulating them in 3-dimensional space to see if they are superimposable can be very challenging. So in this case, my suggestion would be that you use a molecular model, official or unofficial, whatever you prefer, but something that will serve as a visual guide um, throughout this chapter as you get used to changing from 2 dimensions to 3-dimensional. Chirality most often results when a carbon atom is bonded to 4 unique groups of atoms. Here, for example, we have a methyl group, that's a CH3, an ethyl group, 2 carbon atoms, a hydroxyl, and a hydrogen. Now, when you have these 4 substituents in one carbon atom, you can place them in one of 2 configurations. This one on the left or this one on the right. It's always going to be one or the other. If you try assembling this with a molecular model kit, you will see that no matter how you start, how you think you're doing something different, if you rotate enough times, you will fall into one of these two, the molecule or its mirror image. When an atom, like carbon, forms a tetrahedral center with 4 different groups attached to it, it is called a chiral center. In this case, let's analyze each of these examples to see if they are chiral centers. So we're looking at this carbon atom first. You have carbon, you have a methyl group, you have an ethyl group, you have chlorine, and you have hydrogen. Because they are 4 different groups, you can have that molecule plus its mirror image. It is a chiral center. Looking at the one in the center, here you have an ethyl group to your left, a propyl group to your right, to the front you have hydrogen, to the back you have hydroxide. Therefore, another chiral center. Here, this carbon atom, it looks like it's not super obvious. Let me show you. First you have bromine, then you have hydrogen, then you have 1/2 of a hexagon and another half of a hexagon, but because you have a double bond here to the right, that makes it a different substituent. Therefore, you have 4 different substituents. You have a chiral center. So these are all examples of chiral centers. Now here, this is a good practice, and I would like for you to pause this video, take some time to identify and label all of the chiral centers in the vitamin D3. I'm going to give you one, and then I would like for you to kind of work on identifying the others. If you see here, you have hydroxide in this carbon atom. You're going to have hydrogen. It's not explicit, but we know that there's a hydrogen there. And then we have 2/2 of a hexagon. Here you have your double bond, and then here is sort of continues throughout the rest of the molecule. That will make it a 2 different substituents. Therefore, it will be a chiral center. Some stereoisomers can also be classified as enantiomers. Enantiomers are 2 molecules that are mirror images but are not superimposable, therefore not identical. Only a chiral compound can have an enantiomer. So when you have 4 different substituents, you can have it or its mirror image, kind of like what we saw a few slides ago. Enantiomers are different compounds, so they must not have identical names. So we need to find a way to differentiate between one and its mirror image. They have opposite configuration at their chiral center. So for that, we use what we call the Can-Ingold prelog, named after the scientists that developed this model, to designate each chiral center as having either an R or an S configuration, rectus und sinister, right rotating or left rotating, clockwise, counterclockwise. If a compound has the R configuration at a chiral center, then the enantiomer will have the S configuration. R or S is assigned to a chiral center using a stepwise procedure. Just like everything you see in organic chemistry, it is going to be objective and it's going to be very mechanical. That's what we shoot for very mechanical. Using atomic numbers, prioritize the 4 groups attached to the chiral center. 1, 2, 3, and 4. Arrange the molecule in space so that the lowest priority group faces away from you. Now this part here, the numbering isn't really the challenge, it's how to visualize, how to rotate the molecule so that that lowest priority group faces away from you. That to me is the biggest challenge, and I advise that you practice this several times so that you can get that idea in your head, that you can go from 2-3 dimensions, because that's not something we're used to doing. So it may take a second. Count the group priorities 1, 2, and 3 to determine whether the order progresses in a clockwise or counterclockwise direction. If it's clockwise, we assign the R configuration. If it's counterclockwise, we assign the S configuration. And like I've mentioned before, a handheld model, a molecular model, will be actually pretty useful at this point. So let's use this as an example. Here we have a chiral center. We have 4 substituents going by atomic number. Chlorine goes first, followed by oxygen, then carbon, then hydrogen. So in this case, the lowest priority is already in the back. So I will go 1, 2, 3. This is clockwise. This would then be the R configuration. Arrange the molecules in space so that the lowest priority faces away from you. We already kind of did that. Counting the priorities, clockwise is R, counterclockwise is S. So if you're going, in this case, you actually, this is the mirror image of the one we just did, 1, 2, 3, so it's counterclockwise. This would be the S configuration. When the groups attached to a chiral center are similar, it can be tricky to prioritize them. This is one of those times when you sort of stop and start looking at everything on a case-by-case basis. You start analyzing each group separately. The 1 and 4 groups are obvious, but there is a tie for priority in orders 2 and 3. So in this case, we have carbon, hydrogen, and hydrogen on both of these, so we move to the next group. In this case here, we have carbon, carbon, and then hydrogen. Here we will have carbon, hydrogen, and hydrogen. Carbon will have higher priority than hydrogen. That will be your tiebreaker. That would allow you to assign this site number 2 and then this site number 3. First layer, second layer. If that happens, if you go after one layer, you have the same exact configurations. You keep going until you find a tiebreaker. If they happen to be identical all the way throughout, then you don't really have a chiral center. There has to be a difference at some point. That's what we're looking to find. When prioritizing for the CAN-INCO pre-log system, double bonds count as 2 single bonds. So in this case, for instance, we have a carbon atom, 2 bonds, 2 oxygen, so it will be oxygen, oxygen, and hydrogen as the substituents. And that's how we will go about numbering them. Let's review. For using the CAN-INCO pre-log rules, assigning R and S configuration, first we identify the 4 atoms directly attached to the chiral center. Second, we assign a priority to each atom based on its atomic number. The highest atomic number receives priority number 1, and the lowest atomic number receives priority number 4. If 2 atoms have the same atomic number, move away from the chiral center, 1 atom at a time on each side, looking for the first point of difference. When constructing lists to compare, remember that a double bond is treated as 2 separate single bonds.